Okay, let's talk about quantum computing. Alrighty, we are on quantum computing part 5. So if you are new to the channel, new to the series, I have all of my notes on Discord. So I usually take notes and write from our books that we're following for this quantum computing course. We're following.
Happen to have some gray coupons?
I'm gonna leave that in the YouTube video. I just think that's fantastic. We're following the Nielsen and Chang excellent book on quantum information and computation. And if you're following along in Twitch chat, you can do !Discord and grab my notes from the discussion series notes channel. Or if you're on YouTube, you can just check the description below for the Discord invite. Today's lesson is going to be a little bit shorter. It's been kind of a nutty day with everything from audio issues to making me do 40 push-ups. And but here we are. We're finally here at Quantum Computing Part 5. Last time we discussed how quantum computers. Firstly, I'm assuming everybody who wants to look at the notes is there by now. That's kind of like a good thing. I try to stall while people like get there if they're interested in it. But last time we talked about how quantum computers can simulate classical algorithms using what's called a Toffoli gate.
That's rubbish.
The Toffoli gate, of course, we wrote like this. And where we had 2 control qubits and 1 target qubit. And the different variations of the Toffoli gate, remember we talked about where like if we had like some states here. So this was just the general Toffoli gate. We had an A state, B state, B state. And then some other state. I don't know. We'll call it. I don't know what we call it. C, I guess. Who cares? Because the Toffoli gate, different variations of the Toffoli gate were ones were variations where like you could reconstruct classical computation gates based off of you know what you chose for these. So for the NAND gate, we had one setup for the fan-out gate. We had another setup. Okay, so after that, we learned about quantum parallelism, where you know we introduced what was called a U transformation, and what we could do is take some state like after we put it through a Hadamard, where we get I don't know why I'm making these circuits so stinking long. It's just so unnecessary. Where we had some state, and like we started with this example, where if you took the 0 state, here was an X and an X, and then this U transformation will take this Y state and apply a modulus 2 addition with an f of x function, and then out we would get a new state.
You ripped your pants.
I didn't rip my pants. I hope. I hope I didn't rip these pants. I don't think they're ripped. And such that when we did that, we found that you could actually, hold on, I need to make quotation marks when I say this statement, because it's not, I don't want to give anybody the wrong idea. So what happened was,
the knees.
We said the knees are fine. Do I have to take TTS away? Man, I will take it away. I will turn this car around. You guys. Okay, so here's the state, and we got a superposition of a function where it was, you know, we could evaluate the function f of 0 and f of 1.
I dare you. Just take it away from Tyrion.
I could do that. That's a bad. Let me get this word out. We could evaluate the 2 functions simultaneously using quantum parallelism. And that was kind of helpful, right? That was kind of interesting. What did we do with it? Well, we saw the Deutsch's algorithm, which had a pretty lofty quantum circuit. Man, my arms are jiggling like jello. Here we go. And then we had a transformation here. And we did the U transformation, the U transform. And what did we get? At the end, we sent this one back through another Hadamard gate. And this one came, and we got another state here, 3. So what happened here is we broke this up into different states. We had a psi, a 0 here, a psi 1 here, a psi 2 here, and then a psi3 at the end. And then we broke it up into the different steps. Now, it might be helpful on mod Tyrion. It might be helpful if you look at the notes from last time as well, when we get towards the end of today's discussion, because we're going to be using what happened in this a lot for today. This wasn't technically a proper algorithm. There were some issues with it. I don't want to say issues with it. It's still technically a proper algorithm, but there's better things than we could do with this. This is more of a general form of the algorithm that we're going to do today. Okay? And this was done, of course, by David Deutsch. You joined Ray? Yep, we're just finished with the last time. The Lord giveth and the Lord taketh away. So this is called Deutsch's algorithm. But now, Deutsch wanted to do something different, so he came up with what was called Deutsch's problem. And Deutsch's problem is what we're going to solve today. Okay? And in order to solve this, we're going to need the proper quantum algorithm, which is technically Deutsch. It's Deutsch. I think it's Jozsa. Am I pronouncing that right?
Someone
Algorithm.
please do something about Tyrion.
Says Tyrion. Okay.
He needs help.
So the Deutsch-Jozsa algorithm is the algorithm that we're going to use to solve it. Let me tell you what Deutsch's problem was. Okay? And of course, we're going to need to enlist the help of Alice and Bob, our canonical duo. I don't know if that's the right word. We'll just go with it, though. Deutsch's problem. Alice is in Amsterdam. Okay? Again, I'm reading from the notes that I pretty much took directly from the book for this part. Alice is in Amsterdam, and she wants to send a number to, and the numbers run from 0, so the numbers that Alice needs to send, x is an element of the set of 0 to to 2 to the n minus 1.
Helga is in Amsterdam.
And then Bob is in Boston, so she needs to send one of these numbers to Bob in Boston one at a time. So that's the problem. She got to send the number to Bob, okay? And then that's not the problem. Well, the problem is that Bob is going to apply some function f of x, and then send it back to Alice. So Bob is going to apply some function f of x and then send that result back to Alice. But here's the thing: f of x can only equal 0 or 1. Okay, that's it. The f of x is only going to be equal to 0 or 1. And the thing is Bob has to follow a couple strict rules. Okay, so f of x is either going to be balanced, which means it's going to be half zeros and half ones, okay? Or it's going to be constant. So all zeros are all ones. But it doesn't have to be either one. So that's the issue, and you can generate all sorts of functions that follow these two rules, okay? But Bob's not going to tell Alice which one it is, okay? Alice, the point is, Deutsch's problem, the point is can Alice figure it out, and how does she figure it out? Well, classically, Alice would need to send 2n. So let's do it classically. Classically, Alice would need to send 2n over 2 plus 1 letters. Because at any, the balance, it doesn't matter what halves are zeros and what halves are 1. As long as half are 0 and half are 1, it doesn't really matter. So if Alice sends, 2n divided by 2 letters, then there's still the chance that the next one, you could do that and get 2n divided by 2 zeros, and then the next letter get a 1, and then realize that it's supposed to be balanced. You know what I'm saying? So that's the classical way, is Alice has to send 2 to the n divided by 2 letters. So if n is equal to, 500, she has to literally send more letters than atoms in the universe. So that's a problem. How about quantumly? Quantumly, I'm gonna quantumally. That's a new word I'm making up. That's my word. How do we do this here? TM. There we go. Quantumally. Quantumally, Alice can achieve her goal with one letter. One letter. That's a big difference. Quantumally, TM. Yeah, so quantum mechanically, she can do that with one letter only. And our goal is to figure out how. Okay? So, let's do it. Now, here's the thing is like there's a couple things that have to change with this, right? Firstly, Alice and Bob have to agree to send qubits, okay? Because of course it's quantumally. And secondly, the second thing that has to change is Bob has to apply the function in a U transform, okay? So those are two big things that, are going to affect the outcome quite a bit. So let's draw the circuit, okay? Similar to Deutsch's algorithm, there's going to be one major difference with Deutsch's algorithm with this one, and that is that Alice is now going to have 2 to the n qubits, 2 to the n minus 1 qubits or whatnot. So let's get this all drawn up. I probably could have left it up actually, now that I'm looking at it again. And then, so let's do the Hadamard gates. Remember, this is the n tensors. So if you remember this, that means that there's going to be a Hilbert for each, a Hadamard gate for each of the 0 states. So there's going to be n 0 states, okay? And there's going to be a Hadamard gate tensored with each individual state, okay? And then this is just one Hadamard gate because there's only one. And again, we're going to have to evaluate it at different spots, okay? So here we have psi 0, here we have psi 1, here we have psi 2, and here we have psi 3. Just like last time, the goal is to find psi 3, okay? Maybe NC, I don't know. So there's going to be n amount of 0 states tensored together, and this Hadamard is going to be applied to all of them. And then we're going to send it, and then this Hadamard is just going to be applied to the one bit. And then this is the qubit that Bob is going to send through the U transformation. And then there's going to be this state right here, and then Alice will take this Hadamard back, and then we'll get to the psi 3. And when we get to the step to go from psi 2 to psi 3, that's a really good spot to look at the notes from last time, because it's a little bit tricky if you're not watching the notes from last time. And they don't even show it in the book at all. So let me see here. So let's start with psi 0. Psi 0 is just going to be equal to the 0 state n times the 1 state. No, well, that's what I said, right? That's what this means. So there's n 0 states and 1. So that's that. Good. Now we're going to apply a Hadamard gate to both of these. Okay? So this is very similar to the step we did the last time, the first step. And we get the sum from x as an element of 0 and 1 now, n times. Because even though there's n states, we're still only going to let x be 0 and 1 for the quantum bits part, right? You can't have a qubit that's not a 1. There's actually some ways to write it like that if you see it in the literature, but it means something different, and I don't really know off the top of my head what it means exactly. It's like you can write... Oops. Someone was sharing it on a different Discord server that I'm in, and I didn't see the notation before, but apparently if you have like 0 n states, you could just write a state of n. So like if you have 0, 0, and there's n of these, then that you can write like this. Which I did not know that, and we're not using this notation here, so let's not be confused by that. I've never seen that notation other than the paper that someone shared. I don't know how common that is. So anyways, so here we have psi of 1, and it's just applied to the Hadamard gates. Nothing too crazy. I missed something, didn't I? No, I haven't missed it yet. Okay, cool. Now, the next function is the function f is evaluated by Bob in Denver, or in Boston. Wow, and Denver. He's in both places at once. And it takes x and y to x and y modulo base 2 of f of x. I don't know if base 2 is the right word. Modulo 2 addition with f of x, okay? Mod 2 addition is basically you add up the two equations, and you get, if you add up the two numbers and divide by 2, the modulo is the remainder, okay? I've never seen it either. Seems confusing. Same, right? I thought the same thing. Seems definitely weird. Hi, Piano Fist. Welcome, welcome, welcome. And if you are new to the channel, this is not a class setting. This is not a classroom setting, so feel free to ask questions. This is only for the Twitch viewers, so feel free to ask questions. Yeah. You can use the command that's right there. And if it's not related to the discussion that we're talking about right now, I can answer it afterward. And all of these things are on YouTube. So if you want to get caught up with where we're at, all of the VODs are on YouTube. And this one will be on YouTube sometime later. Let's see where we at then. Okay, so we did the function that's going to take the U transform that's going to take x and y to this other state. And then what do we get? Well, just like last time, again, we haven't really done too much different now except for the fact that there's a lot of states as opposed to one state. And we're going to get something really, really similar where we have the x state, square root of 2 to the n, and then we get this one, which is the Hadamard gate applied to the 1 state down at the bottom. And really, Bob is going to be worried about this state right here, right? Bob is going to be applying the U function to his state, okay? So that's really where he's going to be encoding all the information into all of the other states. So now Alice is going to reapply a Hadamard gate back. So this, if you remember from last time, this is the U transformation. It kind of like moves the bits around a little bit so that they're a little different. What does U do? U takes, so that last week was a lot about what U was. But really quickly what it does is it takes this state and it applies it here. So f of x is gonna be like, and this is why the notes from last time are really helpful, because the f of x is gonna have a couple different values. We're gonna have x and f of x. And if there's only one version of x, which is what we did last week, you have 0, 0, 1, 1, where this is 0, 1, 0, 1. So these are the 4 options we had. And then you could apply each of them to here. So like, what happens if this is 0 and this is 0? Well, then you get an answer for that. What happens if this is 0 and this is 1? You get another answer for that. What happens if this is 1 and this is 0? You get a different answer for that, and then likewise with 1 and 1. Okay? So you really consider every single option, and then we wrote them all out and really focused on what they could be, right? So, and again, the modulo 2 is like if y, so y is equal to 1, right? So y is equal to 1. Oh, not after the Hadamard gate. After the Hadamard gate, it's going to be a superposition of 0 and 1. So there's going to be like a 0, and a 0, and then the f of x function as well. So if this is 0 and f of x is 0 and x is 0 and f of x is 0, then you're just going to get 0 divided by 2. So this modulus right here is going to be 0. But then if x is 0 and y is 0, then, and f of x is 1, then you get something different, right? You get, 0 plus 1 mod 2, which is 1. Okay? Bye, Admiral. Okay, sounds good. So like logical function on each input. I'm not 100% sure what the logical function is. I'm sorry. Maybe someone who knows more about it, Bachman or someone who knows more about what the logical function is, or Tyrion even. You could remind us if that's correct or not. But let me keep going, Strawberry. If there's more issues, we can talk about it in Discord afterwards. Yeah, unfortunately, you might have to watch last week's to really know that answer, because, like I said, my knowledge of logical gates is pretty limited, unfortunately. Okay, so let's keep going. Where are we at? Okay, so now we're going to apply the Hadamard gate again. So now we're over here. So we're going to apply n Hadamard gates to the rest of the bits. And remember, if you flip-flop back and forth with the Hadamard gate, if you flip back and forth with the Hadamard gate, it's itself, right? So Hadamard, squared is the identity. right? And we want to make sure that, so when we flip it back, we're gonna end up getting the identity again, but now it's gonna be all sorts of different because we're gonna have to consider multiple versions of the state, right? After we encode this transformation, right here, then all of the 0 states are going to have the information that Bob was messing around with this, okay? And then getting it out in a Hadamard, applying the Hadamard again is going to give us a different outcome. So if we take the Hadamard and just apply it to one of these x's, okay, we're only going to be doing the one of the x's. What's the options? Well, last time we saw that you're going to get a 0 or a 1, so now we're going to represent both of those by a z. And because of that, there was some xz where like this was kind of like controlling the sign. I think last week we saw it as a, let's see if I can write it down from last week. So if you're looking at last week's, it was psi of 3. Psi of 3. So this is very much the same thing right here. And last week we wrote it something like this, where we had a plus or minus the 0 state multiplied by 0 minus 1 divided by root 2, or plus and minus a 1 state where we had 0 minus 1, divided by root 2. And this one was for if f of x or of 0 is equal to f of 1, and this was for f of 0 not equal to f of 1. So this is what we did last week, and this is the same thing except now instead of writing it, oh man, PG Porta. Oh. Okay, we'll get it after the lesson. I owe you guys 10 more push-ups. Don't forget it. Okay. If my body can handle it. Now, this is like a concise way of writing all of this down. Okay? Except instead of
That is 20 more push-ups.
20 more? 10 more. Nice try there. Nice try. I'm watching you. we won't. Okay, so let me erase this. This was just the fast notation for writing this down. This is going to be really helpful because we need to write like a condensed form of this, because when we apply all of those Hadamards, like this is only one Hadamard, but now once we apply all of the Hadamards to X gates, what are we going to get? Or whatever the gate is that we have, you know, the one that Alice has. We're going to sum over all Z, where we have minus 1 x dot z. Oh wait, I missed it. Hold on. I skipped a step. We're at x1 z1 plus dot xn zn, all applied to the z gate, divided by square root of 2 to the n, and the z is going to be z1 plus plus zn. There we go. So now this is, if you apply it to all of them, remember the last time, like I said, we only had that 1 plus or minus 1, 0 or plus or minus 1. And then this time now we have n versions of that, so we're going to have all of these, okay? So this will be boiled down to something very simple. And like you guys, you guys can spend some time with the math and work on it yourself. But I think the cool thing is we can't lose sight of what's actually happening, because what's actually happening here is wicked cool. And you guys are just gonna have to stick around until we get to the end. I think it's pretty mind-blowing actually, that you can do this with a quantum computer, under some caveats. So now if we just take this, we can write it down in even more condensed notation, just say sum over all z, square root of 2 to the n, and where this is a z, x dot z is an inner product, and it's inner product mod 2. Okay, so you're going to be adding up all of these values, and then just at the end you're going to add 2, or mod 2, excuse me. And then that will be in. So, let's see what else we have here. So therefore, we can write our last state. And I think we're almost to the end of today's stuff. This is pretty wild what we're about to see. So you do this and you get the sum over all z, sum over all x. We're writing all of the same thing because now you have sum over all z, but you still have to sum over all of the x's as well when you get to here, like applying it to this state. And what do we get? We get minus 1 to the inner product of x, z plus f of x. And this is, if you've been following along, this is relatively attainable. Like, I don't want you guys to think that this is like super mysterious, because it's not. Like, you can follow the steps pretty coherently through the notes, but there is some stuff that you might have to work out on your own, as I did. Like, I didn't understand this one at all, and I had to sit there and try to figure it out, and it took me a little while, but I was able to figure it out, and I think you guys can do the same thing. You can be confident that you can go back to the Psi 3 from last week and figure out that this represents the same thing. And then once you do that, like, I had to go through and work through this too, and it was, again, it wasn't the easiest thing to do, but I think you guys can do it as well. Okay, so now we're here in this last one. This is Psi 3. So here we have this little bit right here is going to be of main concern right here. Remember last week, all we wanted to do was measure this front bit, and then we could figure out whether or not z and f of 0 and f of 0 was equal to f of 1, or if f of 0 was not equal to f of 1. That's what we figured out last week. Let's keep the circuit up, I think. Coherent. Choice of words, I suppose. I think it's kind of interesting that Bob's information is stored here, right? The thing that Bob took, the thing that he did when he applied this unitary transformation right here, all of that information was stored all in the beginning there. So that's really where we have to pay close attention to, is once Bob takes his one bit here and applies this transformation to the bit, then and he applies his f of x, for how many ever x's there are, and then it will all be encoded right here, even after we do the Hadamard back. Doing the Hadamard back again is basically changing the basis into something that we can measure, which is what we want to do, right? So we're going to measure that basis, and we're going to think about one state specifically, which is what happens if all of Alice's bits, the zeros, are back to the 0 state. Okay? Let's talk about the amplitude. The amplitude of this, if all of the x's are zeros, the amplitude of this is going to be the following. It's going to be the sum over all of x minus 1 to the f of x divided by 2n. Okay? Now, we don't know what f of x is yet. That's important. We don't know what f of x is yet. But we can already start to see that we're going to be able to get some information out of this thing, the amplitude. So let's talk about what happens in the case that f is constant, okay? If f is constant, then for every single value of x that we put in, we're going to get constant. We're going to get the following amplitude, okay? If x is constant, then we're either going to get a plus or a minus on the 0 states, right? So if we measure all zeros and we're going to get plus or minus, then we're going to figure out that f is a constant. But here's the issue. This is a plus or minus 1. That's a probability amplitude. If that's normalized, which it is, there's never been a thing in this where we've taken away normalization. The thing has been normalized the entire time. F is always non-real. Change my mind. So if this is a probability amplitude of 1, what does that mean for the rest of the tensored states together? What's their probability amplitude? Well, if this has a probability amplitude of 1, and we square it, we're going to get a probability of 100%, right? That means that there are 0 probabilities of measuring crickets, I know. We're going to get a 0 probability of measuring anything else. Okay? So that is if f is constant, we're going to measure this either plus or minus, 100% of the time. if f is balanced, that doesn't mean anything, really. This part alone doesn't mean anything, okay? Just because we measured plus or minus this, you're only gonna get one basis anyways. So if you measure it and you get all zeros, you don't know anything from just this piece of information. However, if f is balanced, then that means half of these are gonna be minus 1, and half of them are going to be plus 1. So when we sum over all of them, if it's balanced, this is going to be 0 times 0 state, balanced to the n. Every other state will be a non-zero value. Okay? I think every other state will be a non-zero value. It doesn't really matter if any other state's going to be non-zero value, because if you measure any other state, you know it cannot be this. So if, oh, let me write the phrase. Here's the cool part. If you measure if you measure this out front here, so you measure this, the z state, right? If you get anything other than all zeros, it's balanced. If you get all zeros, it's constant. So Alice was able to figure out from one measurement of z, whether or not Bob's function was balanced or constant. That's it. That's crazy. One letter, one measurement, one letter containing all of the bits, one measurement of one state, and she can tell whether or not Bob's function is balanced or if it's constant. Now let me remind you one thing about Bob's function. If it was a classical setup, she had to send 2 to the end divided by 2 plus 1 letters before she could tell whether or not it was constant or balanced. But with this situation, one letter, one measurement, completely done with the problem. She knows whether his statement was constant or balanced. Okay? Now, if you look through the notes, you can see that I have, I don't know what you guys in computer sciences do, but if you look at the Discord and the notes, I have all of this, I have like a little bit of an algorithm. I don't know if it's like proper or not, but it's what they wrote down. It's just sort of the algorithm that outlines what we did. So I'm not going to go and put it on the board because it just seems redundant to put it in both places. But it is there, and it's just sort of, it outlines the algorithm that we used to figure out this problem. But there is a few caveats. Are you going to finish or what? Come on. Focus. There we go. So there's a few caveats with this, right? The first one is there's actually no known applications for this. So if you are feeling very clever, maybe you could come up with an application where you can apply Deutsch's problem to a real world thing. You're good in time for caveats, yeah. The second caveat is that quantum and classical algorithms are pretty different. So like while, so it's not 100% fair to compare the two, like the two algorithms. Like you can't, this is what the authors say. It's not 100% fair to say that Alice needs to send 2 to the n over 2 plus 1 letters to Bob in order to figure out whether or not his function is constant and balanced, or whether or not she needs to just send 1 letter and then measure 1 state to figure it out. So while it's really cool and nothing should be taken away from the outcome here, it's not very much of a fair thing in like terms of like energy cost or things of that nature. It's a little bit different. And lastly, Alice could also find success using probabilities, right? Alice can just do the same thing as this and do probabilities with significantly less letters than 2 to the n over 2, and all classically. But the problem with that is it's still just probabilistic. There still could be a chance she's wrong using that. Whereas this, it's 100% f is constant if you get zeros, f is balanced if you get anything else. And that's it. Either way, like the authors say, either way, it's a solid demonstration of how powerful this quantum computing can really be. It is really, really nifty what they're able to show here and what Deutsch and Jozsa were able to show and how they were able to solve this one problem this very specific way in a very clean and concise way. But that's it. Quantum mechanics quantum computation part 5.